Hello, welcome to Physics 104A. This is the homework solutions for Chapter 5. Number 11 says two forces, both in the XY plane, act on a 3.25 kilogram mass that accelerates at 5.48 meters per second squared in a direction 38 degrees counterclockwise from the x-axis. One force has a magnitude of 8.63 newtons and points in the positive x direction. Find the other force. Let's first draw a picture. You can see my picture there. It just gives us an indication of which way the mass is going to go. I've written out the given information. We have the mass, the acceleration, and the direction. We know that the net force is mass times acceleration. So when we multiply mass and acceleration, we get 17.81 newtons at a 38-degree angle. So let's break that down into its x and y components, magnitude times cosine and magnitude times sine. So we know that the net force as a vector is 14.034 newtons and 10.96493 newtons. Now we're given that one of the forces, we'll call it F1, is 8.63 I hat plus 0 j hat newtons. So we're just going to set up the equation that the sum of the forces is the net force. So here we have in this line 8.63 and 0 plus the mystery force F2x and F2y equals the net force. And so then we find that the x and y components of the mystery force that I'm calling force 2 are 5.4 newtons in the x direction and 10.965 newtons in the y direction. So now we can write that in vector notation, rounding to three significant figures, 5.40 I hat plus 11.0 j hat newtons. And here I've drawn the force, and you can see it's the same direction, 38 degrees, as my original drawing that described the acceleration. Number 12. Two forces act on a 3.1 kilogram mass that undergoes acceleration of 0.91 I hat minus 0.27 j hat meters per second squared. One force is negative 1.21 I hat minus 2.5 j hat. What is the other force? So this is very similar to question number 11. Here we have the addition of the forces, and we've got the mystery force there that we're trying to solve for, equals mass times acceleration. We multiply mass and acceleration, we get the net force on the right-hand side, and then we just read across. The top gives the x components of force, the bottom gives the y components of force. So we're just going to solve that and figure out what those values are. So we get, from the top line, we get F2, the x component, is 2.821 minus the negative 1.2 newtons. And the y component of F2 is negative 0.837 minus negative 2.5. And so we end up with 4.0 I hat plus 1.7 j hat newtons. Number 14. A skier starts from rest at the top of a 24-degree slope, 1.3 kilometers long. Neglecting friction, how long does it take to reach the bottom? When you're dealing with a physics problem on an incline, there are two different equations, and one deals with friction, one does not. This one says neglect friction. So we're going to use the equation A equals G sine theta. I'm not showing you the derivation, although in a later problem, we'll be doing the friction equation for acceleration, and I'll show you that derivation. But we'll just go ahead and use this equation that on a frictionless slope, acceleration is G times sine theta. So we take G multiplied by sine of 24 degrees, we get an acceleration of 3.986 meters per second squared. Now we do the kinematics. V naught is 0, displacement is 1300 meters, we want to know the time, and so let's do x equals 1/2 at squared, solving that for time, square root of 2x over a, and we get 26 seconds. Number 18. There's a picture given in the book. I've broken the picture up into two separate force diagrams. It says, suppose the angles shown are 60 degrees and 20 degrees. If the left-hand mass is 2.1 kilograms, what should the right-hand mass be so that it accelerates? Part A says downslope at 0.64 meters per second squared, and B upslope at 0.76 meters per second squared. Let's draw a force diagram on each of these. And so on the left side mass, you see what I've done. I've made the x direction go up the ramp. You can see normal force and tension going up the ramp. And then these are the x component and y component of weight. And I derived those in class. And in a later problem, I'll show where those come from. And on the right-hand mass, I've made the x direction go downslope. And so you can see the tension in the rope, which is T. It's the same tension in the rope as in my first diagram. Normal force and the x component of weight and the y component of weight. Now, for both objects, you can, as I've written here, I've made the positive direction be such that object 1 goes up and object 2 goes down. Now, it doesn't necessarily have to be that way. They could go in the other direction, but I wanted to make them consistent so that if mass 1 goes up in the positive direction, mass 2 will go down, also the positive direction. But if they go the other way, then they'll just be in the negative direction. But I wanted to keep those both consistent. All right, let's look at the force diagram and apply Newton's second law to the object 1 on the left. F of x equals mass times A of x. I'm just looking at the x component now. So we have tension in the positive x direction minus m1g sine theta 1 equals m1a. I'm going to solve for tension. And so tension equals m1 g sine theta 1 plus m1a. For object number 2, I apply F equals ma in the x direction. We have m2 g sine theta 2 minus tension equals m2a. I want you to see, as I've written there in blue, I haven't distinguished between A1 and A2 because if they're both connected to each other, then their accelerations are going to be the same. So I just call them A. So here are the two equations that I get from Newton's second law. I'm going to go to the next page and I'll put those equations on the top of the page. All right, so there are the diagrams. There are the two equations. You notice I have two equations that are both showing equivalence for tension. Since they're both equal to expressions that are equal to tension, let's set the two equations equal to each other and then solve for one of the masses. We're going to solve for m2. So setting those equations equal to each other, m1g sine theta 1 plus m1a equals the one on the right, m2g sine theta 2 minus m2a. And so I'm going to go through and solve for m2. We already know what m1 is. It's 2.1 kilograms. And here we have m2 as a function of the first mass, the acceleration, and the two different angles. Now we can plug in the accelerations. Part A says, what if the right-hand mass goes downslope? So let's remind ourselves what direction that is. We look at the picture, and I started by calling that the positive direction. So acceleration is going to be positive 0.64 meters per second squared. We plug that into the equation for m2, and we get 7.1 kilograms. Now part B says it accelerates upslope. So acceleration is negative 0.76 meters per second squared. And you can see its mass is going to be much less. So the mass on the left is going to pull it. And in this case, M2 is 3.9 kilograms. Number 21, show that the force needed to keep a mass m in a circular path of radius r with period t is 4 pi squared mr over t squared. Okay, so just a derivation here. Let's start with F equals ma. If we're talking about circular motion, F equals mv squared over r. And we know that we're going to have to involve periods somewhere because that's what the question is asking us to do. So let's remember that going around in a circle, the speed is circumference over period, so 2 pi r over t. Now let's make that substitution. So for v, we plug into the force equation, 2 pi r over t squared. And then we clean it up and we make it look like what the question is asking for. So we get 4 pi squared mr over t squared. Number 27. A hockey puck is given an initial speed of 14 meters per second. If it comes to rest in 56 meters, what's the coefficient of kinetic friction? Let's draw a force diagram. It's moving to the right. We've got normal force up, mg down. And force of friction is to the left, that kinetic friction. F equals ma in the horizontal direction. We see the one horizontal force is negative friction equals ma. Remember that friction is mu sub k times normal force. And if we look at the y components, we see that normal force is equal to weight. So N equals mg when you're dealing with a horizontal surface. So we're going to replace N with mg. The m's divide out, and we're left with mu sub k is negative a over g. All right, but now we need to find acceleration. So let's look at the kinematics. It says that v naught is 14 meters per second. It comes to rest, so v equals 0. Displacement is 56 meters. With that information, we'll use this kinematic equation, v squared equals v naught squared plus 2a delta x. Solve with respect to solve for acceleration, and we get negative 1.75 meters per second squared. Once we get that, we plug that into the mu sub k formula, and we get 0.18. Number 28 involves going down a slope with friction. Starting from rest, a skier slides 100 meters down a 28-degree slope. How much longer does the run take if the coefficient of kinetic friction is 0.17 instead of 0? All right, we need an equation for acceleration with friction. Here's the complete derivation. I did this in class. We have F equals ma in the y direction. That leads us to normal forces mg cosine theta. Now, we're assuming that the skier is going down the slope, and you can see friction is negative, where the x component of weight is positive. So here we have w sine theta minus friction equals ma. And by the way, if the skier were going up the slope, friction would point in the opposite direction. So there would actually be a plus sign here because friction would point to the right. But here it is going down the slope. And let's clean this up. Weight becomes mg, and then sine theta, minus friction becomes mu sub k n equals ma. Then we replace n, normal force, with mg cosine theta, and you can see mass is a factor in every term, so we can divide mass out. What we get is the equation acceleration equals g times sine theta minus mu sub k cosine theta. And this is an equation worth remembering rather than having to derive it again. I'm going to use this equation in later on. All right, here we've got the equation. And we're going to plug in theta is 28 degrees. We plug in mu sub k is 0.17. We get the acceleration, plug it into that formula at the top, and we get 3.1298 meters per second squared. However, if there is no friction, we go back to the equation a equals g sine theta, and we get an acceleration of 4.6008 meters per second squared. So the friction creates less of an acceleration. Now we're going to apply that acceleration to the 100-meter downward slope, and we're going to see what it is with friction and without friction. We use the kinematic equation delta x equals 1/2 at squared, solve it for time. So time is the square root of 2 delta x over a. With friction, when mu sub k was 0.17, we solve for time and we get 8 seconds. Without friction, the skier is going to get down there more quickly, and you see it's 6.6 seconds. So it will take 1.4 seconds longer with friction. Question 30, a multi-body problem. A 63.2 kilogram climber finds herself dangling over the edge of a cliff. And there was an example earlier in the book, and you can see my picture right there. Fortunately, she's connected by a rope of negligible mass to a 1220 kilogram rock located 48.6 meters from the edge of the cliff. Unfortunately, the ice is frictionless, so the climber accelerates downward. What is her acceleration? How much time does she have before the rock goes over the edge? You can see the picture that I've drawn. I've made plus x and plus y directions in the direction of acceleration. So let's look at the big rock, the boulder, and we can see the forces acting on it, tension pulling straight to the right, normal force, and the weight of the rock. And I've made the direction that it's going to accelerate plus x. The climber, with another force diagram, is going to accelerate downward, and I've made that plus y. Just so we keep the math consistent, so we don't have to worry about one of them has a positive acceleration, the other has a negative acceleration dealing with that positive and negative. I've made them both have exactly the same acceleration with the same magnitude. It's going to be positive. You can see the force diagram on the climber. Let's look at the force diagrams and apply F equals ma in the direction of motion. So for the rock, the sum of the forces in the x direction is mass times acceleration, and I've used big M for the mass of the rock. So the one force pulling in the x direction is tension. Tension equals big M times A. For the climber, remember down is the positive y direction, so the weight of the climber minus tension equals little m times A. Weight of the climber, I've made little m times g, and then minus t equals ma. And now I'm going to substitute in, we already know that tension is the mass of the rock times acceleration. So let's substitute that in right here. And we get an equation that is little m times a plus big M times a equals little m times g. So this equation will be useful throughout the problem. Now, we want to know what is acceleration, so let's solve this algebraically. For acceleration, we'll factor out little m plus big M, and then we get acceleration is mass of the climber over mass of the climber plus the rock times g. So you can see that acceleration is going to be decreased with a much larger mass of the rock. If the rock is much, much more massive than the climber, that's going to decrease the acceleration. So in this case, acceleration given their masses is 0.48267 meters per second squared. Now let's see how much time she has. Displacement is 48.6 meters. That's how far the rock has before it goes over the edge. And so once again, we use this kinematic equation, delta x equals 1/2 at squared. Solve for time, and she has 14.2 seconds before the rock goes over the edge. Number 31, a similar problem. Says the rock is located 48.6 meters from the edge of the cliff and help is on the way. Unfortunately, it will be 36.5 seconds before help arrives, and the ice is frictionless. How massive must the rock be if she is to be saved? So it's the same setup as the last problem, but now we're solving for big M, and we're given a time. So I just wrote C number 30 for the derivations. I won't go through all the F equals MA again on the rock and the climber, but here was the result in the middle of the page. Little MA plus big MA equals MG. Let's solve for what the acceleration needs to be in order for help to get there on time. She has 36.5 seconds. The displacement of the rock is going to be 48.6 meters. And so we can solve for what its acceleration needs to be limited to if to make it take at least 36.5 seconds. And so we'll use the kinematic equation one more time. Delta x equals 1/2 at squared. We're going to solve for acceleration and get a slow 0.072959 meters per second squared. Now with that, we're going to solve for the rock's mass because that's what the question is asking for. We'll take this equation that I derived in problem number 30. We're going to algebraically solve it for big M. So the mass of the rock is the mass of the climber times G minus A divided by A. Plug in those values and we get that the rock needs to be 8430 kilograms. Number 39, a block is launched with initial speed 2.2 meters per second up a 35-degree frictionless ramp. How far up the ramp does it slide? All right, it's frictionless, so we'll use the equation acceleration equals g sine theta. You see my picture there. I've made up the ramp be positive. V naught is 2.2 meters per second. V is 0 because we're looking for it coming to a momentary rest. Now acceleration is g times sine theta. However, look at the direction that I've drawn it going. I've drawn it going up the ramp. You know that gravity is going to pull it down the ramp, so acceleration is actually in the negative direction. So here I'll use acceleration as negative g sine theta, and we get negative 5.621 meters per second squared. We use the kinematic equation to see when v equals 0, so v squared equals v naught squared plus 2a delta x. Solve for delta x, plug in the values, and you get 0.43 meters is how far up the ramp it'll go. Now, question number 49. A child sleds down an 8.5-degree slope at constant speed. What is the frictional coefficient between slope and sled? Because the child is sliding down at a constant speed, there's no acceleration. That tells you right there that there is friction. If it were frictionless, the child would be accelerating at acceleration equals g times sine theta. But constant speed means friction is taking away from that acceleration. We use the equation A equals g sine theta minus mu sub k cosine theta that I derived in an earlier problem. Problem number 28. And in this case, constant speed, acceleration is 0. Now the question is asking for what is the coefficient of friction. So we'll take this equation and solve it for mu sub k. We have sine theta minus mu sub k times cosine theta equals 0. I just divided both sides of the equation by g. Get mu sub k by itself. And you get mu sub k equals sine theta over cosine theta, which is tan theta. So mu sub k is the tan of 8.5 degrees, and so 0.15. Number 52. A bat crashes into the vertical front of an accelerating subway train. If the frictional coefficient between bat and train is 0.86, what's the minimum acceleration of the train that will allow the bat to remain in place? Well, let's look at a force diagram of the bat. Now, as the train is pushing the bat along, the accelerating train, you can see that there's a normal force between the front of the train and the bat. So normal force goes to the right. There is the weight of the bat pulling it down, and there's friction, which is dependent on the normal force that is pushing it up. Here I've made x go in the positive right direction, positive y go up, we're given that mu sub k is 0.86. And we want to know what is the acceleration needed to hold the bat in place. Let's look at F equals ma in the x direction. The only force in the x direction is normal force equals mass of the bat times acceleration. Let's now look at F equals ma in the y direction. We want zero acceleration for the bat. So the friction up minus mg down equals acceleration of 0. You know that friction, in this case it's static friction, u sub s times normal force, minus mg equals 0. And here I'm going to do a substitution. Instead of normal force, we learned up here, circled in purple, that normal force is, for this problem, mass of the bat times acceleration. So let's plug that in here. And we can see that the mass of the bat is irrelevant. We can divide the entire equation by m. What we get is mu sub s times a minus g equals 0. And so acceleration, solving algebraically, is going to be g divided by mu sub s. So 9.80 meters per second squared divided by 0.86, we get that the train needs to be accelerating at least 11.4 meters per second squared in order to create the normal force, which leads to the friction that will keep the bat up. Number 58. A police officer investigates an accident. He estimates that a moving car hit a stationary car at 25 kilometers per hour. Before the collision, the car left 47-meter-long skid marks as it braked. The officer determines that the coefficient of kinetic friction was 0.71. What was the initial speed of the moving car? We need to find the deceleration of the car. And so we have the sum of the forces equals ma. We look at the force diagram and we see that kinetic friction as the skid marks were laid down as it slid across the street. So minus F equals ma. We're replacing friction with mu sub k normal force. Let's replace normal force with mg. And so we have negative mu sub k mg equals ma. The masses divide out. We're left with the acceleration is negative mu sub kg. And so we plug in those values and we get negative 6.958 meters per second squared. Now we're going to apply that acceleration, or the deceleration, to the 47-meter long skid marks, and we're going to see what its initial speed was. Well, we know the final speed, we know acceleration, we know displacement as it skidded along, so let's find the initial speed. We'll use this kinematic equation, solve it for v naught, we get v squared minus 2a delta x, and we get 26.5 meters per second. It's appropriate because the question gave the information in terms of the car hitting at 25 kilometers per hour. It's appropriate to give an answer in those same units. So we'll convert this back and get 95 kilometers per hour. And that is the end of the Chapter 5 homework. Have a great day.